So I've been asked to do a video about laminas. I'm not sure laminas are going to come up, but I'm, as you know, a bit of a completist, so I like to make sure we've covered everything. I think the sort of problem that's going to come up with moments, and that's the thing that's listed on the pre-release under statics. I think it's going to be a ladder question, but it could also be one of these sort of hinged questions. Friction is mentioned, so that's why I think it could be a ladder question, although there is one question I've recommended you try where there's no hinge, and so you've got friction between a rod and a wall. Definitely make sure you've done the static questions that I've suggested in a separate document. But yeah, so these sorts of questions are pretty straightforward. Well, no, they're not straightforward. But the moments part of it is straightforward because we're dealing with just a single rod or a bar or a ladder. So when we want to work out moments, we can just think about perpendicular to this rod. So let's say I want to take moments at about that point there. I've got the weight of the rod, but we don't know where it is. It's non-uniform. So let's call it X. And it's 100 newtons. So it's not 100 G, it's already a force. So that's 100. If its mass was 100 kilograms, we'd put 100 G, but there we go, it's 100 newtons. We've got a tension in the cable, which is 80 newtons. And we're told it's in equilibrium. And we've got to work out this distance here. So we can think perpendicular to the rod. So this force, the weight, is already perpendicular. And this force, we just think about its perpendicular component, which is 80. I know that angle is 60. So that's 80 cos 60. Or 80 sine 30, whichever you prefer. There is a horizontal component of that force, 80 cos 30. But when we're dealing with moments, we don't have to worry about that because that is acting directly in the line of A, so there's no distance from A. So there is a horizontal component to that force as well, but we only really need to worry about the vertical component. So I take moments about A, and I like to say, clockwise equals anti-clockwise. You see some textbooks or some work examples that make clockwise negative and anti-clockwise positive and say they have to equal 0. Doesn't really matter. But in this case, the clockwise moment, pulling it clockwise, is this. So that's 100 times x. And the anti-clockwise moment is that force there. Times the distance forward. You know what? I so often forget to put the distance in because I think I've already multiplied two things together. But no, that's the component of the force. And we can then rearrange that to make x. You might just want to pause and have a go at that. So you get x. X is 1.6 meters. Okay, so that's a classic example of moments. And as you know, most statics questions, whether it's a ladder or a rod, they involve a combination of taking moments and then horizontal and vertical resolving. Or if it's on a slope, parallel and perpendicular to the plane. There we go, that's that, or parallel and perpendicular to the ladder. So let's have a look at a laminar question. So a laminar is when you're dealing with something that isn't just one-dimensional, but two-directional. And something that is a laminar, it has a weight, so there is a weight to it, but it doesn't have any thickness. Now, actually, this question here, we don't consider the weight at all because it's a boat that's floating, and we're looking down on it from above. And we're encouraged to take moments about P. So how do I deal with the fact now that I'm not just dealing with a single rod or a single ladder? Well, we think parallel and perpendicular. So this force here, like in the previous question, is acting sort of perpendicular to this line here. So the twisting effort of that force, if I take moments about P, well, it's going to be 5,000 times that distance there. This force here, well, that's sort of acting parallel to that line, isn't it? So what I'm going to do is continue that force line. It's parallel, and actually I can think of it acting here with a distance of 30, because we're told B is the midpoint. So that's a sort of a parallel force. So here I'm working out its effective distance from the pivot by continuing the line. So that force, and it's a bit hard to get your head around this, but that's another, sorry, this force here was pulling it anti-clockwise. This will have a clockwise effect. And then you've got this force here, which has a vertical component, and that angle there is 40, so that's going to be 6,000 cos 40. It does have a horizontal component, but that horizontal component, unlike this one, which is acting at a distance of 30 metres, that component is acting at a distance of 0 metres. So when I calculate the moment, the distance is 0, multiply force times distance, there's no moment at all. So if I now take moments about P, well, I've got this force, which is pulling it clockwise, anti-clockwise, and then I've got this force and this force pulling it clockwise. And in this question, it's not in equilibrium. So one is going to win. It's either going to be turning clockwise or it's going to be turning anti-clockwise. So I've got this force and this force, which are acting perpendicular to this line. And then I've got this force, which is acting parallel to that line. And I can work out the moments by working out force times that distance. Just see if you can work out which wins, clockwise or anti-clockwise. Pause and have a go. Okay, so I've rounded this one to the nearest whole number. Newton meters, because it's force times distance. And clearly, anti-clockwise is winning. So the anti-clockwise moment, which is acting perpendicular to that line, is 5,000 times 240, and that is much, much bigger than the two clockwise moments composed. So this boat is going to twist in an anti-clockwise direction. Now, why did I pick this line here? Why didn't I pick this line here? Well, I would have got exactly the same answers. This force would have been acting perpendicular, and these two forces would have been acting parallel. You would have got the same answer with exactly the same calculation. The key is that this lamina, these two forces are acting at right angles to the lamina. This force is acting at an angle, so I'm breaking it down into its two components. I don't need to worry about this component because it's running through the pivot point, so there's no moment. This is the only one I need to worry about. Okay? So do you want to have a go at this question here, which is a sort of similar question, but involves an angle? So have a think about what's going on here. This time, we've got a mass. It's a uniform lamina, so the mass acts exactly at the centre. So that's got a mass of 12 kilograms, so its weight will be 12g. So what I encourage you to do is to think about turning this into a problem like the last one with the boat. All right, we've got this force has two components. One that is in this direction, I'm going to call that perpendicular to the lamina, and this one which is parallel to the lamina, although it would be the other way around if I was considering this side. This force is acting perpendicular to the lamina, So I'm going to just take moments about A. This is going to be an anti-clockwise moment, but so is this, the component of that force. This force is going to be a clockwise moment, and we're told in this case that it's in equilibrium. So go on, see if you can have a go at that question there. Okay, so I took my diagram and twisted it, and that meant that this, which is actually vertical, is going a little bit that way, and that angle there is 20. It's the same as this angle here. So that means that angle there is 70. So this 12G force, if I square up the lamina, has a component in this direction, which is 12G times the cos of 20. I know it looks a bit like 30, but it's 20 with an arrow. 12G cos 20, and 12G cos 70 going in this direction here. So there are three forces in this diagram. I've got this force here, the tension. Remember, I've taken that diagram and just twisted it. So this force here, and that's acting at a distance of 6. And that's an anti-clockwise one. This force here, which is also anti-clockwise. So if you imagine, pulling it that way, pivoting it there, and that's acting at a distance of 1 meter. That's another anti-clockwise one. And then this force here, which if it's pivoted there, is pulling it clockwise, and that's acting at a distance of 3. So I did that. Only one clockwise moment. This, 12G cos 30 times 3. And the two anti-clockwise moments, T times 6 and 12G cos 70. And look, I put the bracket. I told you I keep forgetting to use the distance. Please don't fall into that trap. Fortunately, the distance was just 1, so it didn't actually make any difference, but there we go. Please don't forget to do force times distance with moments, and then it's just a little bit of algebra to get the answer. So in this example, this force has components both vertical and horizontal, but we can ignore the horizontal one because that's acting at a distance of 0 from the pivot point. In this case, no, it's not acting at a distance of 0 from the pivot point, so we had to consider both of the components of this, and squaring up our diagram allowed us to do that. Okay, so have a go at this final example. A little bit trickier because the force holding this, I'm sorry, that was a mistake I found, that should be 10 newtons. The force holding this lamina at an angle is not perpendicular to the lamina itself, so that's an extra level of complication. Remember what I recommend you do: twist it and then work out the components of this force. So there'll be one in this direction parallel with that edge, perpendicular to this edge, and then a component in that direction, perpendicular to that edge, parallel with this edge, and then the same for this force, which has a component in that direction and a component in this direction. However, this component is running through the pivot, isn't it? So its distance from the pivot is 0, so actually we don't have to worry about that one. In terms of the angles, well, this angle is alpha. So what I think about is, I think if this was originally lying flat and then was tipped up, that arrow would have swept through that angle. So that angle is alpha. And then also using parallel lines, I know that those two angles are the same. That's alpha. So that angle there is also alpha. So anyway, have a go at that question, pause, and I'll come back with a solution in just a moment. Sorry, just to say, these are in centimetres, and acceleration is in metres per second squared, so you've got to use metres, so that's 0.03, 0.05. Right, carry on. Okay, so I started by resolving the forces, so this component is 2g cos alpha, and this component, because I don't know this angle, I have to use sine alpha. That's 2g sine alpha, and this force is acting at a distance of 2.5 centimetres, and this force is acting at a distance of 1.5 centimetres. You've then got this component of the supporting force, which is 10 cos alpha, and that's acting at a distance of 3 centimetres. So it's always the distance we're after is the distance perpendicular to the edge of the lamina. And then so this force and this force are clockwise, so I've put force times distance, doing my distances in metres, and then this force is pulling it anti-clockwise, so I've done that. And then it's just algebra. It's quite fiddly, but I just collected all my coses on one side and factorised sines on the other, and then divide by cos gives you tan, divide by that, and that gave you the angle. So there we go. As like I said, I don't think laminas are going to come up, but I'm a completist, so I like to make sure I've covered the bases. And anyway, it's good practice at this whole idea of resolving forces into their different components. Okay.